Rational functions review. Graph and analyze rational functions limited to numerators and denominators that are monomials, binomials, or trinomials. So a function that can be written in the form f of x equals px over qx, where px and qx are polynomial expressions, qx cannot equal 0 because you cannot divide by 0. So if we look at the following equation, y equals, this one here, y equals 2x over x squared plus 2x, we know that we have to factor our denominator. When we factor our denominator, we get an x and an x plus 2, and then a 2 times an x. If our x's cancel off, that's a point of discontinuity. Point of discontinuity at x equals 0. How do I find the y? Well, I'm left with 2 over x plus 2. Y equals that. So I'm going to do y equals 2 over, but x is 0 in this place, so 0 plus 2. So y equals 2 over 2. So y would equal 1. So y equals 1 when x equals 0. So that's why my point of discontinuity is at 0, 1. So on the graph at 0, 1, I have a point of discontinuity. On the denominator, after I cancel that point of discontinuity off, I'm left with x plus 2. Well, that would leave me with a vertical asymptote because it didn't cancel off. So I have a vertical asymptote at x equals negative 2 as well. And then when I'm left with my equation, after I cancel off my points of discontinuity, I'm left with 2 over x plus 2. Well, I know that if this is degree 0 and this is degree 1, if the numerator is smaller than the denominator, I have a horizontal asymptote at y equals 0. So that's why I have that. And I draw the rest of my graph, making sure I leave my point of discontinuity. Now my domain would be x such that x can't equal negative 2 because of the vertical asymptote, and 0 because of the point of discontinuity, XER. My range is going to be y such that y cannot equal 0 because of the horizontal asymptote, and 1 because of the point of discontinuity, YER. Remember that your vertical asymptotes come from the denominator, whatever, if it doesn't cancel off, you solve those out and get the vertical asymptote because your denominator can't equal 0. And in this case, if I have x equals negative 2, it would cause the denominator to be 0. If the factors cancel off, it's a point of discontinuity. But then there's rules for horizontal asymptotes, which follow here. So if the degree of the denominator is larger than the degree of the numerator, so in this case, it's degree 2 on the bottom and degree 1 on the top, my horizontal asymptote is y equals 0. In the previous case, I had degree 0, 2x to the 0 over here, over x to the 1, so it was y equals 0. If the degree of the numerator is equal to the degree of the denominator, you take a fraction of the coefficients for your horizontal asymptote. So that's why I got a over b. And if the degree of the numerator is greater than the degree of the denominator, you have no horizontal asymptote. Okay. So we're looking at the function, a rational function in this form. The form we've just looked at was y equals, you would put your x-intercept and an a value in front over your vertical asymptote. And you'd have to solve for that a, remember? Or if you have a point of discontinuity, it's a times your x-intercept times your p of d over your vertical asymptote times your p of d. But your entire equation, numerator is over denominator. So that's the one format. And if we have a p of d, we have to use this form. We can't use the other form. This is the other form. This is your transformation form. A is your vertical stretch. Your vertical asymptote is based on this because that's your horizontal translation, h right. So your normal asymptote, the reason why that works is on a basic graph of y equals, or 1 over x, you have asymptotes on the y and x axis. So if you have any transformations horizontally, so in this case, h to the right, my asymptote is going to move h to the right. So that's why my asymptote is my horizontal translation. And my vertical translation, k up, normally it's on the x-axis. Now it would move k up. So that would get me my asymptote. So that's why my vertical translation and my horizontal translation get me my asymptotes. So if it's in this format, whatever your horizontal translation is your vertical asymptote. And whatever your vertical translation is your horizontal asymptote. So it depends on what form you're in. If you're in the form where the entire numerator is over the denominator, or if you're in the form where it's in that transformation form. If you have a point of discontinuity, I want to repeat, though, that you have to use this format. This form only works if you have a vertical or horizontal asymptote, but not if you have a point of discontinuity. Okay, graph with or without technology or rational function. So we're going to sketch the graph of the following function, determine the following characteristics for each function. Domain, x and y intercepts, equation of vertical asymptotes, any non-permissible values. So we can factor the denominator. What multiplies to give me -6 and adds to give me 5. It's going to be x plus, or x, oops, it's going to be x plus 6. X minus 1, because that's the opposite sign. Nothing cancels. If nothing cancels, I don't have a point of discontinuity. I do, however, have vertical asymptotes, because these don't cancel, they're my vertical asymptotes. I have a vertical asymptote at x equals -6 and 1. Also, the numerator is a smaller degree than the denominator. This is degree 1, denominator is degree 2. So I have a horizontal asymptote at y equals 0. How can I find the rest? Well, if I want my y-intercept, I have to set x equal to 0. So y would be, so this is my y-intercept. I could also pull it off my calculator, but I'm going to show you how to do it algebraically. So you're going to get 2 times 0 over 0 squared plus 5 times 0 minus 6. So you're going to get 0 over -6. And you can go 0 divided by -6. That's 0. You just can't divide by 0. So my y-intercept is at 0, 0, which indirectly my x-intercept is also at 0, 0. So I'm going to have an x and y-intercept at 0, 0. How can I get the rest? Well, I can type them into my calculator. Now I can pull my calculator up here, but I'm going to type it into my calculator, and I'm going to type the entire numerator in a bracket and the entire denominator in a bracket so that my calculator knows what is the numerator and what is the denominator. And then I'm going to go to my table of values, second graph, and I'm going to pull off values. So I'm going to take values from the left of -6 because there's going to be graph on the left of -6. So I have -7. Lines on here. I have -7 and -1.75. I'm just taking this off of my table of values on my calculator. -8 and -8 and -0.88888 up here. -9 and -0.6. -10 and -0.4. And we're getting closer and closer to the x-axis, so it's going to roll along like this and come down the asymptote. Then we have -5 and 1.667. We have -4 and 0.8. -3 and 0.5. -2 and 0.3. -1 and 0.2. We have 0, 0. And then we have an error. So what's happening is it's this. And then I'm going to pull values on the opposite side of 1 because that's where it's going to start again. 2 and 0.5, 3 and 0.3, 4 and 0.2, and so it's running along here and along here. Okay, my domain is going to be everything but -6 and 1 because that's where it doesn't exist. The easiest way to write that is x cannot equal -6 and 1, but x is an element of the real, so it's every other number but those. And the range is going to be y such that y is not equal to 0, and everything else is fine. So y, yeah. So let's look at the next function. Okay, so if I factor the denominator, I have to do decomposition. 2x squared plus 5x minus 3. What multiplies to give me negative 6? Now it's going to be 5. In this case, it's the same factors as before, but we have to do decomp this time. So I need plus 6x minus 1x minus 3 group. Plus 9. So I'm going to get 2x, and I'm going to get x plus 3. I take out a negative 1, and I get x plus 3. And so I get 2x minus 1, x plus 3. So in my numerator, I have 2x minus 1. And in my denominator, I have 2x minus 1 and x plus 3. If you're noticing right now, the 2x minus 1's cancel. If they cancel, it's a point of discontinuity. So I know I have P of D when x equals a half, because I have to solve it out. But what is my y? Well, if this cancels off up here, these little lines that cancel and cross are actually 1s. So I have y equals 1 over x plus 3. From there, I know I have a vertical asymptote at x equals negative 3. I know I have a horizontal asymptote at y equals 0 because the top is degree 1 and the bottom is degree, or top is degree 0 and the bottom is degree 1. Now I'm not going to plug this into my calculator and look at it because it won't encompass my point of discontinuity. If I want to look at my graph, I actually have to plug the original in. But this form where I've simplified it, I can actually plug the half in and get what my y is in my point of discontinuity. So I'm going to get a half plus 3. So I'm going to get y equals 1 over, and then it would be 1 half plus 6 over 2. So y equals 1 over 7 over 2. And when you divide by 7 over 2, it's like multiplying by 2 over 7. So my point of discontinuity is at a half and 2 over 7. Remember, solving for that point of discontinuity is actually a standard of excellence. So I'm going to type the original into my calculator just so I can pull off other points in a little bit. So I'm going to put the top in brackets and the bottom denominator in brackets. So I get 2x squared plus 5x minus 3 bracket. Press graph. Look at it. I know I have a vertical asymptote at negative 3. So I'm going to put that first. I know I have a horizontal asymptote at y equals 0, which is the x-axis, because the equation of the x-axis is y equals 0. And I know I have a point discontinuity at a half and 2 divided by 7. 2 divided by 7 is like approximately 0.29. So I know at a half and 0.29, I'm going to end up with an open dot, which is kind of hard to draw. So there's an open blue dot there. Then I'm going to pull values on the left of negative 3 and on the right of negative 3. And negative 3, I should have an error, which I do. So if I go to negative 6, it's at negative 0.33. Negative 5 is negative 0.5. Negative 4 is negative 1. And it just runs along. There. Then I go on the opposite side, negative 3. So I have negative 2 and 1. I have negative 1 and 0.5. I have 0 and 0.3. Then it goes down to 0.28 approximately with the 2 over 7. 1 and 0.25, and so it's running along like this. So my x-intercepts do not exist. They didn't exist on the other one either because I have an asymptote on the x-axis. I don't always have an asymptote on the x-axis, but in these two examples I did. Now my y-intercept is at 0 and a third. And I just pulled that from my calculator. Now my domain is actually going to be x such that x cannot equal negative 3. And most people stop there because they forget about the point of discontinuity. But it also doesn't exist at a half. XER. My range is y such that y cannot equal 0. And you can't forget the y of the point of discontinuity, 2 7s. So everyone forgets about the point of discontinuity. Don't be that person because you'll have the answer there for that. All right, this one says determine if the graph of a rational function will have an asymptote or a hole, point to discontinuity for a non-permissible value. So for the graph of y equals 2x plus 5 over 5x minus 4, determine the equation of the horizontal asymptote and the range. We're not getting a point of discontinuity because 5x minus 4 does not cancel. If I solve it out, I get 5x minus 4 equal to 0, 5x equals 4, divide by 5, x equals 4/5. Now, that's a problem because that value, if I plug it into my denominator, is going to make my denominator 0, which actually makes it a non-permissible value. So that's why the domain would be x cannot equal 4/5. Okay, so this is my vertical asymptote, just going over it. Did we need my vertical asymptote? No, we needed my horizontal asymptote. My horizontal asymptote, when you have an entire numerator over an entire denominator, follows the rules. If the degree of the top is smaller than the degree of the bottom, it's y equals 0. If the degree of the top is the same as the bottom, which this one is, I take a fraction of the leading coefficients. So my horizontal asymptote, because y equals lines are horizontal, because the y equals 0 line is the x-axis, which is horizontal. My horizontal asymptote is going to be y equals 2/5. And then my range is just going to be, it can't equal that because that's where the asymptote is. And the asymptote actually is the place where the graph doesn't exist. So it's going to be y such that y cannot equal 2/5, y-er. Okay. Determine the coordinates of the point of discontinuity. Okay, so this one we have to factor the top. So we have 3x squared minus 2x minus 1, which we have to do decomp because there's not a 1 in front of the x squared. What multiplies can be negative 3 and adds can be negative 2. It's going to be negative 3x positive 1x minus 1 group. Take out a 3x, you're left with x minus 1. Take out a plus 1 because I can't take anything out. Left with x minus 1. So when I factor it, I get 3x plus 1, x minus 1. And that's in my numerator. So I get y equals 3x plus 1, x minus 1 over 3x plus 1. The 3x plus 1's cancel, and I'm left with just y equals x minus 1, which will help me get my point of discontinuity y value. I have no vertical asymptotes because my denominators are all gone. That means I also do not have a horizontal asymptote because they are besties. If I do not have a vertical, I do not have a horizontal. So I know I have a P of D only, because my denominator's gone now. I have no more issues. X cannot equal negative 1/3 because if it did, my denominator would be 0. But this results in a point of discontinuity. How do I find my y? I plug it in. So I get negative 1/3 minus 1. Y equals negative 1/3 minus 3 over 3, which equals negative 4/3. So my P of D is actually at negative 1/3, negative 4/3. Now, the graph of the function below can be expressed in this form. What is it? So remember, you need to use this format here. So my point of discontinuity happens at x equals negative 2. So on the denominator, I'm going to have x plus 2 because it has to be the opposite. In the numerator, I'm also going to have my a, and I'm going to have my x-intercept. My x-intercept is at 4, so I'm going to have x minus 4. And then my vertical asymptote goes on the bottom, and my vertical asymptote cuts through negative 1, so I'm going to have x plus 1. Now I take a point, plug it in, and solve for my a. I'm going to use my y-intercept, which is 0 and negative 4, because it crosses through quite nicely. That's my x and my y. So I'm going to get negative 4 equals a. 0 minus 4, 0 plus 2, 0 plus 1, 0 plus 2. Yes, you could cancel off the 0 plus 2s if you'd like. They can go away when solving for a, but they have to be there when you're actually solving the equation out. So we get negative 4 equals a times negative 8 over 2. Bring the 2 up. Negative 8 equals negative 8a, divide by negative 8. And this is the best thing that could possibly happen, a equals 1. So if you forget to solve for a, you'd be golden. But we don't want to just have that happen. So we're going to have y equals 1, x minus, x plus 2 first, sorry. Because if you look up here, the first two are the matching ones. So x plus 2, x minus 4, x plus 2, x plus 1. And then they could say, what's a plus b? What's b plus c? What's the sum of a plus b? What is, put a and b in ascending order, descending order, whatever they want to say. Okay? So this one says, determine graphically the approximate solution. So we can solve these algebraically, but I'm going to go over how we could do them graphically just as a little reminder. Algebraically, you can remember from grade 11, you would cross multiply. So you do this times this times this, but I'm going to show you with your calculator. So we're going to do these with our calculator. When we put them into our calculator, we have to put the left side equals in Y1 and the right side in Y2. I'm going to show you how to do it graphically because that's an outcome. And I want you, most people can solve properly, but forget how to do it graphically. Numerator has to go in its own brackets divided by the denominator, which was x plus 4. And then the right-hand side is going to be 4x divided by x squared minus 16. Graph. We have to find out where they intersect. So there's two intersections. So second trace 5, enter, enter, enter. So my one solution is that I'm going to go back here and I'm going to go x, math, enter, enter, and see if it turns into a fraction. It doesn't. I'm going to keep that on there. So it's approximately, x is approximately negative 1.77. And I'm going to put that in the answer in a second. And then I'm going to go second trace 5. And I'm going to find, oops, second trace 5. And I'm going to find the other one, closer to the other one over there. And I'm going to enter, enter, enter. And I get 6.77. So negative 1.77 and 6.77. Oh, positive 6.77. Then I'm going to check the other one. So we have y, clear these out, and then we have 7 is our left. That was all that was there. And then on our right, we're going to have bracket x squared minus 7x plus 12 divided by x minus 5. Second trace 5. Zoom 3. I know I need to have it cross at 7. So I don't know what my window's at. Zoom 6. I don't want to press Zoom 3. There it is. So second trace 5. I know I have a horizontal line at 7, so I need to be able to see that at the very least. Enter, enter, enter. And I get 8.41. Just writing it on my whiteboard. And then second trace 5. Move over to the other one. Oh, I did it again. Second trace 5. That's that blue line. Move over. Enter, enter, enter. And I get 5.59. I think the other one was 8.41. I'm just going to check. Second trace 5. Enter, enter, enter. And remember 8.41. You can pull it onto your normal screen. You can go second mode and just press X, enter, and it'll pop up your last X you found. We don't care what the Y's are. We only care what the X's are. So we have X equals 8.41 and 5.59. That's it.